Section 6.4 Inductors. An inductor consists of a coil of conducting wire, and you can find the typical form of an inductor in the middle of the slide. And there are n turns of wiring. The length is L, and the cross-section area is A. And there is a core inside the inductor, and the permeability is mu. And you can find three types of practical inductors in the slide as well, which are toroidal inductor, solenoidal wound inductor, and chip inductor. You can find the symbols of inductors in this slide. Graph A is for air core inductors, and graph B is for iron core inductors, and graph C is for variable iron core inductors. And the relationship between the voltage across the inductor and the current through the inductor could be represented like this: V equals L multiplied by di over dt. That means inductance is the property whereby an inductor exhibits opposition to the change of the current flowing through it, measured in henries. And you can use a capital letter H for the henries. And on the other hand, you can calculate L like this: L equals n squared multiplied by mu multiplied by A over L. Okay, now we have already know the relationship between V and I, and we can draw a graph to represent the relationship between them. And we can write di like this: di equals the reciprocal of L multiplied by V multiplied by dt. And we get I equals 1 over L multiplied by the integral from minus infinity to t with respect to v tau multiplied by d tau. And finally we get this equation: I equals 1 over L multiplied by integral from t0 to t with respect to v tau multiplied by d tau plus it0, where it0 means the current when t equals t0, and we call it as initial condition. And we can calculate the power absorbed by the inductor like this: P equals V multiplied by I equals L multiplied by di over dt multiplied by I. And then we can calculate the energy stored in the inductor. And finally we get W equals 1 over 2 multiplied by L multiplied by I squared. We should know the important properties of an inductor. The first one is the voltage across an inductor is 0 when the current is constant. That means an inductor acts like a short circuit to DC. The second one, an important property of the inductor is its opposition to the change in current flowing through it. So the current through an inductor cannot change instantaneously. For the two waveforms in the graphs, the first one is allowed for an inductor, but the second one is not allowed because the second one is not continuous. The third one, the ideal inductor does not dissipate energy at all. The fourth one, a practical non-ideal inductor has a significant resistive component. You can find it in this graph, and you will find an Rw in series with the inductor and a capacitance Cw in parallel with it, where Rw is winding resistance, usually very small, and the Cw is winding capacitance, is very small and can be ignored in most cases. This is the end of this section.